Hello everyone. So myself Suman Jyoti there. But before beginning this talk, I would like to thank the organizers for giving me this opportunity to talk, present my work here. So I will talk about this emergence of spin active channel at a quantum Hall interface, and this work has been published in this PRB letters, and you can look at the details for the talk. This work has been done in collaboration with Ganpati Murthy and his former student Amartya Saha, my PhD advisor Sumati Rao, and Ival Geffen. Okay, so this is like a brief overview of my talk. I will give a brief introduction of what is the edge reconstruction in quantum Hall system, and then I will talk about the model we are interested in, and then I will talk about the bulk of the system without edge, and you can do some analytical calculation even in the presence of the electron-electron interaction, and then you can find there are some robust phase transition, and then I will talk about the Hartree-Fock result, self-consistency theory with edge and edge or interface, what we call, and in presence of electron-electron interaction. So let me begin of the simple introduction of now in the quantum Hall context. So we all know that the charge degrees of freedom are gapped in the bulk of the integer quantum Hall system, and there exist chiral gapless edge modes, and this can be understandable from the semi-classical picture of cyclotron orbits in presence of perpendicular magnetic field. So there are cyclotron orbits in the bulk that makes a closed orbits, but when you go close to the edge, semi-classically, they have some skipping orbitals like this, and the resultant will have a net edge current in the system. So this will carry the current if you drive the bias across the system. This bulk topological constant dictates the electrical and thermal Hall conductance carried by the edge mode, but within this constant the edge reconstruction can happen, and it is very much relevant to the experiment. And this edge reconstruction in quantum Hall system has a very long history. It starts from the late 90s, and it's mainly happened due to the competition between electron-electron and electron background electrostatics interaction. So I will give some two simple example where people have found this edge reconstruction. So first is this nu is equal to 1 case, which has been seen by Salmon and Owen in back 1994. So what they found in their work is you put a background charge density that neutralizes the electron density in the bulk, but you can actually, for a very sharp background density, what if you do the Hartree-Fock theory or exact dimerization with a small number of electrons, what you will find that the electron density, so the occupation of the electron just goes from 1 to 0. But if you make this this width with large than a certain critical value, or the background falls very smoothly, then you will see that some part of this electron will actually goes away from the bulk, and it's actually form a separate liquid. So in the system you will find that there are 2 downstream mode and 1 upstream mode, and it can be understandable from this fact picture that if you calculate in this case using this occupation, if you calculate the electron density is actually fairly matches with this background charge. So it wants to neutralize the system. Now for the nu is equal to 2 case, that also has been seen in the same times by Dempsey, Galfand and Halperin. So what they found is here you have both up and down spin in the bulk. Now for a very sharp background, this bulk ends at the same point, both up and down spin. But if you increase this W or make a very smooth potential, what they found is it doesn't no longer the case. So actually what you find is the down spin and up spin actually physically separates. The edge of the down spin and the edge of the up spin physically separates. So what you found is what we find is there is a spin polarized region in the close to this edge. Okay. So with this background introduction, we want to look at a different scenario where mostly the exchange will play some more important role to produce a spin active channel. So what we call by spin active channels, I will go into the details later, but so that is our motivation. So for this reason, what we consider is like a system where there is a left hand side, there is a nu is equal to 4 region, and right hand side there is a nu is equal to 3, and there is a background potential that connects between the nu is equal to 4 and the nu is equal to 3, and we can play with the width of this background potential. So actually the model, if you look at the microscopic model, it has many terms. So first term is the cyclotron energy term, and the second term we have like a Zeeman term, and then we have a electron background interaction term, and this is like the electron-electron interaction term, and we have modeled the background term like this, which falls linearly with a W, such that it has the charge neutrality in both sides, and it mimics the nu is equal to 4 to nu is equal to 3 region. Now we will work with a Coulomb interaction with screened Coulomb. Because of this, there is a, at q is equal to 0, there is a this discontinuity. So we have a like a small, but we have checked with different scanning length. It does, the results we got it's fairly robust in terms of the scanning length. So so before going to the actual result, let me so if you look at this model, what happened is like if there is no edge, you can actually do a Hartree-Fock decomposition of this interaction term. Then you will find that in the bulk, due to the charge neutrality, the Hartree term will cancel by the background term, and you will have only the exchange term. And this exchange term actually wants to make a spin polarized system. So what you will find that for nu is equal to 3 region, it goes from an unpolarized, partially polarized to state to a fully polarized state, and the nu is equal to 4 region. So if you look at the number, you will find that there is a region of space where the nu is equal to 4 is the unpolarized case, and the nu is equal to 3 is fully polarized. So it's like a spin singlet and the spin fully polarized state. So we want to look at this scenario, how these two boundary connects, and and this number will change on depending on the Zeeman field and the scanning length, but there will be a range where this will be the interesting region in our case. So then if you do the self-consistency calculation, we found that there are two robust phases, phase B and phase A. So where the phase A actually will be there for the large W, we will see that the spin of the system is like a good quantum number along the spin quantization axis. But for the phase B, what you will find that the spin will no longer be a good quantum number, and there will be a many body spin rotation in the close to the interface. And okay, so this is like so if you look at the phase in detail, so what we will find that for the phase A, that is for the larger W, you will find that if you look at the spectrum, there are 3 modes crosses there will be 3 modes crosses the Fermi energy, and each time the mode crosses, if you look at the total Sg, it actually jumps in unit of h bar over 2. Like it goes from like unpolarized to a fully polarized state in steps. So, but it jumps in a steps of 1 unit. That it signifies that each mode has a particular spin index along the spin quantization axis, and it doesn't also the Sx also 0. And if you look at the phase B, actually what happened is like in the middle, you will see that there is only one mode crosses the chemical potential. And in this case, the spin actually rotates from 0 to 3 and that if you look at the total Sx is non-zero around this point. So what happened is actually in our case, it's the system, the total spin of in the interface actually rotates in the xg plane, and we have choose our answers such that it's in the xg plane. You can also do it on the yg plane also, but yeah. So, but the main fact is it breaks the E1 spin symmetry about the Zeeman axis for this phase B. So with this, we also can understand this behavior of phase diagram is little more. So what happened is that the phase A, which exists for the larger W, has the 3 chiral modes, right? So if you calculate the electron density, it's like for the phase A with a very large W, it actually mimics the background potential very well. But for smaller W, what happens is like it's like a sharp change of the background. So there is no room of like the electron density wants to change very rapidly, and it can do by via the like a many body spin rotation in the system, and it breaks the E1 spin symmetry here. But if you look at this weird behavior, it's actually happened due to the due to the like spin stiffness cost for this below this point below EC 2.7. The spin stiffness cost increases with the with EC because of the small lambda level mixing. But for higher EC value, it has a large lambda level mixing, which actually decreases the spin stiffness cost. So this phase has a spin stiffness cost. So it's actually so the for smaller EC, the phase A actually expands over phase B, but for larger the EC, it's actually expands because of small stiffness cost. So with this, I want to come to this my conclusion and discussion slide. So if in total we have two phases. The phase A having the 3 charged chiral modes with each Hartree-Fock level gives by the spin quantum number exists for very smooth background potential, and phase B which has a 1 charged chiral mode, but it has a spin rotation in the Hartree-Fock happens for far background potential. But we can also explain these two phases by using some effective field theory in the spin sector. So in presence of the Zeeman coupling along the spin quantization axis, the spin sector is like a XXZ model because the spin there is a Zeeman term in the Z direction that's make the SU2 symmetry to a E1 symmetry in the XY plane. So now, but due to the ferromagnetism, we need this J and delta to be greater than 0. Now, classically, one can find that for this model, if you have a small Zeeman field, for delta less than 1, the classically this system breaks a E1 spin symmetry. For delta greater than 1, it doesn't. So we can say that the delta less than 1 phase is in the phase B of the Hartree-Fock, and the delta greater than is the phase A, where it doesn't break the spin symmetry. So although the very fact that it breaks a E1 spin symmetry, you will have some counter propagating gapless long wavelength spin excitation in space B if you go beyond the Hartree-Fock and include some excitations in the theory. And so we will believe that this can be used to distinguish it from the phase A in experiments. So with this, let me thank you. Okay.
Thanks.
I have a short question. So in all your calculations, is the implicit assumption that the length scale over which the potential varies is much larger than the magnetic length? That's why you can take smooth potentials. So how relevant is that for experimental situations?
Okay. So actually, this is with the W tilde. W tilde is with respect to magnetic length. By magnetic length.
So these are all much larger than 1. So how relevant are these parameters in this window in actual experimental samples?
In gallium arsenide samples, actually the means like in the edge, it's like a very smooth edge actually. But also you can now they can tune with the like gate voltage. You can tune the length of the edge also using by the gate voltage. So it's like you can tune this thing experimentally.
I see.
But these are large in the actual materials also.
Can I ask a short follow-up question? So do we know what happens in the other limit when the this edge potential starts varying very rapidly?
Yeah, so this actually phase extends up to W2. I haven't shown this for like smaller W, but it's
all the way down to W equal to 0.1 or something. I see. Thanks.
Although, but it has some. So if you look at these pictures, we have input some extra levels. Like if you look at this level, these are some extra levels that actually is like doesn't actually have like. Means if you want to say it's like if the cartoon picture what I was saying last time, 1 minute. So if it has like 3 Landau levels with 2 spin, But so in this thing, if you do the calculation with 3 Landau levels with 2 spin, you will see some instability close to W is equal to 0. So for that, to removal of the instability, if you have to include higher Landau level. So it's actually it's stable using the higher Landau level mixing actually.
Isn't it surprising that you don't get a trivial insulator in between at small W?
I think the two sides, the topology is different, right? So it's not will be trivial. Yeah.
What happens outside this EC window?
Oh, the outside this EC window. So above this, actually, this becomes the fully polarized. The nu is equal to 4 side is like fully polarized. So it's like spin will like simply go through it. Like means it will from like up spin to up spin and down spin to down spin. It will like something simply pass through. Yeah.
Okay. So in some sense, this line actually ends.
Yeah.
There. Okay. Okay. Are there any further questions? So if not, let's thank